All right, so more of the mental gymnastics that we have. This one's actually pretty cool to show conceptually what we have going on, so we'll just dive in. The statement reads, in practice, the current typically distributes itself quite uniformly over the wire. How do you account for this? If the positive charges, density rho plus, are nailed down, and the negative charges, density rho minus, move at speed v, and none of these depend on the distance from the axis, show that rho negative equal negative rho positive gamma squared, where gamma is equal to 1 over the square root of 1 minus v divided by c squared. And we know that c squared is equal to 1 over mu naught epsilon naught. This gamma factor should look familiar to those, especially if you're interested in relativity. So if the wire as a whole is neutral, where are the compensating charges located? All right. So first, let's understand that the mobile charges do pull toward the axis, but the resulting concentration of negative charges sets up an electric field that repels away further accumulation. Okay, that makes sense. You can't have too many piled up together. So equilibrium is reached when the electric repulsion on the mobile charge Q balances the magnetic attraction. Makes sense in an equilibrium equation. So then the Lorentz force has to equal 0, and that implies that E equals negative V cross B. All right, fair enough. So then the current is in the z direction, or say the current is in the z direction, and our current density is equal to negative rho v z hat. Again, since we're looking at the negative charges, rho naught and v are both negative, and thus their fields are, use Ampere's law for the B field, you get B equal mu naught rho negative vs over 2, phi hat direction. And then for the electric field, we see that we have from Gauss's law, E equal 1 over 2 epsilon naught, and the total charge, so rho plus rho minus times S in the S hat direction. So if we plug these into the force relation that we just found, and we take the cross product of the current and in the Z hat and the magnetic field with the B hat, or V rather, we see that this is equal to mu naught over 2 rho negative V squared SS hat, which makes sense based on the electric field, so we got a check there. Cancel out the S's, cancel out the 2's, move the epsilon naught over, and we see that the total charge, rho plus rho minus, is equal to rho minus times epsilon naught mu naught V squared, again in the same direction, so we're just worried about a scalar quantity now. But we know that epsilon naught mu naught is equal to 1 over c squared, so we plug that in. Do some more algebra and simplify the fractions. We see that we have rho plus is equal to negative rho minus times 1 minus v squared over c squared, which we know that looks like the Lorentz factor, or gamma squared rather. And so we shove that through and algebraically solve for rho minus, and we get the result that we were anticipating. But in this naive model, the mobile negative charges fill a smaller inner cylinder, leaving a shell of positive stationary charges on the outside. But since V is much less than C, the effect is extremely small. That makes sense.